So this is about Pro3D, and I just want to introduce briefly what is Pro3D. What we do have is a cadence of processing and visualization, and Pro3D is the visualization and analysis part, whereas the ProVip, which is the Planetary Robotic Vision Processing, is a batch stereo and 3D vision processing queue that we had developed throughout, I think, 10 or 12 years now. It's generating digital elevation models, panoramas, other 3D data products from PDS rover stereo images. We have tested and verified it by regular processing of mainly MSL must-come PDS releases, but it's also applicable to other such data like the MER data or Phoenix stereo data. It's planned to be one of the options for the Mars 2020 must-come Z strategic processing. And also for the ExoMars 2023 NavCam, LocCam, and PanCam tactical processing and also strategic processing. So I wouldn't go too much into detail onto ProVip. This is, let's say, call it a black box. It is generating so-called ordered point clouds, which are regular point clouds that are overlaid by diverse layers like RGB texture, like filter images texture, maybe also by distance maps and things like that, and also some semantic information if needed. And this goes into the Pro3D. So the Pro3D is an interactive real-time rendering system that can be applied to huge multi-scale 3D data as expected for Mars 2020 must-come Z and ExoMars PanCam. It provides real-time rendering and gives tools for analysis and annotation, mainly for geology. Now, we have a couple of features which won't be all of them demonstrated, but I try to give an overview on what's available here. We have, of course, the interactive rendering of these multi-scale 3D surfaces. Multi-scale means both rover imagery and remote sensing imagery in different modes, as Thomas will show later on. It provides large context navigation in the 3D scene, so you can, like a drone, you can move yourself, explore, free fly, orbital mode for overall scene understanding. As I said, we are using this ordered point cloud format, OPC, which contains 3D as real Cartesian coordinates in the first instance, but those can be transformed in real time to any coordinate system that you need. At the moment, we do have also geographic coordinate systems ready on that. Now, we have a SPICE interface for that purpose in order to be able to do these transforms on the fly. As I said, we can visualize and navigate in really huge data sets, so it's literally no limits. So we could even start with entire Mars, all the HRSC data, and go into more detail on specific high-rise scenes, and then go further more detail into let's say wide baseline stereo results, and then go into the fixed baseline stereo results, and even on microscopic scale, all together seamlessly zoomed in. We may not show the visual fusion of these different multi-scale data today. Could happen later on if there's time. We can also import and manipulate other data such as wormhole objects, trajectories of rover, 3D point lists, and subsurface radar scans, as you see to the right. That's one additional option we wouldn't show today. We will show the measurement tools for the exact geological assessment of the surface. We will show the analysis today. Now, we have launched this Pro3D Space page, which is containing download information for Windows software. I need to say that the Mac and Linux version have been already developed, but we still need some items to deploy them, so that may take some weeks' time, some further weeks' time, and we will certainly let you know once those are available. It contains tutorial videos, it contains the manual, it contains example data, and it can be used basically in the context of MASCAM-Z and PanCam data exploitation. So anyone from those two science teams that wants to use them, or engineers that wants to use the Pro3D, is invited just to download the software, use the manual, and let us know about your success. And of course, you can also use the data that is being provided there. Now, we will use some specific data today for the demo. Namely, Thomas will use the MASCAM data from SOL 1275 with sequence ID 5976, which is the transition between the Stimson formation and MER formation, as you see here. And as you see also that we chose a lateral resolution of the 3D data product, which is similar to the input data. So we have, I think, 65 different stereo patches, and each of the stereo patches had been processed using the ProVip, and they have been stitched together using SPICE information and TAVOR information. And what you see is the integrated result that Thomas will be using to demo the software. Now, which kind of products were we using for this one? That one element is the distance map in spherical coordinates that we assembled into the OPC, and this is being overlaid by the ortho information, as I said, in a similar lateral resolution as the original data has. Now, I want to introduce to you Thomas Ortner. As I said, he's from VRVIS. He's the head of the Geospatial Visualization, Semantic Model and Acquisition group at the VRVIS. They are dealing with 3D geospatial representations, visual analysis, and they also integrate spatial and non-spatial data, which is, let's say, the measurement data and the semantic data in my terms, as I would say. And now, if there is any questions, please place them in the questions area. If there's any relevant questions that really address my presentation. Otherwise, I would suggest we ask Thomas to proceed with your presentation and give us your demo as prepared. Thank you.
So I start from the very beginning. Thank you for the kind introduction, Gerhard. How do we get Pro3D? You already hinted on that. Just go to Pro3D Space. Then let's click on Getting Started. And here we can just download Pro3D. It will tell you the platform and the current version. It will always link to the latest available stable version. And we just downloaded it here. And oh yeah, I also provided some overview. Before we go into more detail, I will cover a lot of topics in this demonstration. So here's an overview slide that will tell you about how to download and set up Pro3D, how to manage the scene, about navigation, coordination systems, coordinate systems. Then we talk about a bit about measurements in general, some additional features. Then I will show you some geological annotations, and we will conclude the demonstration with two specific sites. The Jezero Crater, and also a demonstration of the Victoria Crater area. And in the end, there will be some further outlook to our MINERVA site project, combining image data and 3D data, and also view planning prototype. This will only be a video I will show you shortly. So we just downloaded Pro3D. We get a zip archive here. Then let's extract it And in this archive, after extracting it, we look for PRo3D.viewer.exe. And when starting that, the console will pop up showing us a lot of information. This is mostly unnecessary. Unless something is crashing, you might get errors here. So for reporting bugs, or if you have any problems, it makes sense to look into this console. So this is an empty PRo3D viewer. We only have the coordinate system in here. And our first task will be to import the data, the 3D data Gerhard was talking about, SOL 1275. For that, we go to the main menu, Surface, and import OPCs. We can also import OBJs, but for now, we will go to this nicer version. Yeah, we can just, I retrieved this data from an FTP site. Usually after just unpacking it, it's a bit difficult to know what an OPC is and what not. So we made this quite straightforward. You just select a folder where you suspect to have an OPC inside, and PRo3D will just scroll through that and find all OPCs in there. So in this case, we only have one, the stereo mosaic here. If it was successful, you will see this here, that here in the root group, we have a new surface. So this is the data shown by Gerhard before in 3D. And you might notice these 4 icons here. The first one is the home button. So when we click on that, we will go to the default importing position. This is just the corner of the bounding box looking at the center. So this is not very useful, especially not in this case. So the first thing we will do is we'll pick a nicer home position. For that, we can just select the surface. You see this, these are actually the patch borders overlaid here. This is our selection highlight to know which surface is selected. And we go to properties and say set home position. And now we have a new home position. Second is open folder. So you always know where your data is. This will open the surface folder where the OPCs are inside. So this is what an OPC actually looks like. It has images and patches, but you don't really have to be concerned with that. You can just import your data on a high-level folder and PRo3D will do the rest. This eye here is hiding and showing it again. And this is not so important. This is for picking interactions. So picking means doing something on the surface. So pick surface, for instance, selects the surface. Every picking interaction has to be preceded by holding down Control. So I'm holding down Control right now, and I can select the surface by clicking it and clicking again, deselects that. So now we have imported a new surface into our scene. We gave it a new home position. So what we want is actually, we want to save the state. For that, we go to Scene, Save Scene, and make a new scene here. Every PRo3D scene is just ends with .pro3d. So saving that gives us here the scene name. And to find our scene again, we can click again on the folder and it will open up this folder again. So as a next step, I will give you some introduction about navigation. I've already been doing this so far. This is the free-fly navigation. You can steer with the mouse. The left mouse button changes the orientation. The right mouse button goes closer and further away when moving your mouse. And the mouse wheel does the same. And the middle mouse button allows you to pan. in this free fly navigation. Also, you can use the keyboard, WASD, like in ego shooter games, which maybe not everybody is familiar with. W and S is going back and forth, and A and D is strafing. Also very useful is with page up and page down, we can change the sensitivity. Pressing this, you can also see here in the view config that the sensitivity is changing. This allows us to navigate large-scale environments or small-scale environments like this one. Then second navigation mode is called the arcball mode. For that, we have to pick a position we want to orbit around, like this rock here, for instance. You can see that the camera jumped a bit. This is because it centers onto the view. So right now we are orbiting around this location here. The controls stay the same actually. This is the mouse wheel, for instance. And if we get completely lost, we can always press the home button, and even in the arcball mode, it will bring us back to this original orientation. Also, when changing back, when changing back from arcball to free fly, the camera is reoriented, so it makes a little jump again. So I don't get confused using that. And there's one more control feature. Don't know if you can see it, but if you have an Xbox controller, you can just turn it on. It also allows for a much smoother navigation for those of you who have this lying around. So these are three navigation modes. Next, we will cover coordinate systems. Gerhard already talked about this. The one which is most useful in this context is the Mars coordinate system. So this is the IAU ellipsoid model. So we are here in a spherical system, and just showing you this in X, Y, Z, it would look like that. So now I got lost, and using the home button brings us back again here. So we can also show here we can place the coordinate system somewhere else. So the red line points towards the North Pole. We can show this or not. We can use different scales. So this is maybe useful also to measure. Sometimes, especially when using this for field trials, there might be some misorientations. So, also for terrestrial outcrops, one can change the north vector and put an offset in degrees here. Also, you might realize we have some additional coordinate system information here. So these are actually the spherical coordinates of the coordinate system in this IAU system, and we are also -4 kilometers beneath the reference ellipsoid. Sometimes if you get data in the rover frame or in some other non-spherical coordinate system, you might use none, which is just XYZ Cartesian, or we also added recently a JPL variant of that, which just has an inverted up vector. And for more details on where you actually are here in the coordinate system pane, you have more information. Also, this is about the camera, like the pitch and the bearing pointing towards north. So we look south, so we're about at 180 degrees. So next we go into annotations. Pick another picking interaction, draw annotation. Here's always the reminder, you have to hold down Control to pick something. We have different geometries here, point line, polyline, polygon, end dip and strike, which I will explain to you later. And these are different projection modes, which I will also explain later. So as a first step, we will just make a point annotation here. Let's go to our rock. Here in the annotation, we have a new point, and we can change different aspects of that, like the size afterwards, or we can also change its color. It's now turned yellow, and we can also give it some text and also change that. This works with all the different geometries, so we can use lines. For drawing a line, we just pick 2 points. And this projection here, there's viewpoint and sky, just tells the system how this line should be connected. So linear is just a linear connection between those two. Sky is like a profile projection. So now this is just projected from above, and sometimes it might be useful to have viewpoint projection, which projects exactly from the camera. So from this view, it's a straight line, but from above, you will see this checked line here. So as a next step, we go more into more useful measurements. So we go back to linear and draw 2 lines, which is probably also the start of a geological analysis, just to check how big an outcrop is. So we make a horizontal line and a vertical one. We can also pick an annotation again. So let's check here, this one. Besides properties, there is measurement data. So interesting here, for instance, is the length of this line. So we are 9.5 meters across, and there's a vertical difference between the 2 points of 40 centimeters, and the horizontal distance is almost the length of the line, so it's quite flat. Same goes for same measurement data is present in the other line, which is 21 meters long and has a much higher vertical distance. And if we check this kind of checks out. Or I hope it does. Of course it checks out. So this is already the first part of measuring an outcrop. Now we can delete this again. Just select the group and then here remove all this. Save our state by pressing Ctrl and S, and our scene is saved. So now I will make a bit of an experiment. Usually when you get a scene from another person, they have different file paths on their machine. Or if you have all your data in an external hard drive and you plug it into a different computer, will have a different volume number, for instance. So what I'm doing now is I will hide our OPC. So opening back up here, opening the PRo3D viewer again. It loads up with the last scene you have opened, so you don't have to look for your documents all the time. It just always opens the last one. So, but we have a little problem here. We use absolute paths, so you can store your OPCs anywhere or also in the central location. But when this little exclamation mark here comes up, PRo3D cannot find your surface. But this is quite easy to resolve. So similar to, I think Adobe products do this, similar to Lightroom. you can tell Pro3D where to look for your surface. So we look in this hidden folder, and there it is back again. So this is quite useful when you're collaborating with other people or if you're changing machines a lot. Then we can also do other things with surfaces. Let's go to our home position again. We have transformations. We have color adaptation. So you can, for instance, change the contrast of the surface, or some features might be more apparent in black and white. This image, for instance, or if you have NAVCAM images or other black and white images and you want to color them, probably not in this color, but in any other color, you can also use these color overlays. Then quite useful is also the so-called triangle filter. So right now, we filter away all triangles that are bigger than 1 kilometer. So this doesn't make, so basically we see all of the triangles, but we can see here some elongated ones and we want to get rid of them. So right now we are culling all triangles in this 3D scene which are longer than 1 meter. For that, it might be interesting to know actually what this surface looks like. So it's made up of all these triangles building the 3D mesh. These are the individual points. Then another interesting feature are bookmarks. So you can save, especially if you want to show a certain location to somebody or just for presentation, you can construct bookmarks. So let's make this one and make another bookmark here. And we implemented smooth transitions between those. Then there are some other yes, in the view config you have some more options like showing our level of detail approach, like selecting the appropriate detail depending on the distance. This is a crucial part for showing arbitrary sized and arbitrary detailed 3D reconstructions. So the gray one is the highest level of detail, and as we zoom out, we dispose this high quality data and show lower quality data. So if you're not sure if you're looking at the highest quality, just turn on level of detail. If it's gray, then it's fine. And also what Rob loves to do is turning on the quality to the maximum, so you still have highest quality even if you're quite far away. Of course, this takes an impact on performance. So let's get to the next topic. Wait, what did I do? Oh, yeah. So now we come to one of the most central geological annotations. We are doing dip and strike measurements. Let's make them white. You also have the possibility to group your annotations. So for instance, we make a new group here and call them cross strikes. Please excuse my geological dilettantism here. I will just make some random annotations here. So after picking the points and pressing enter, we fit a plane to these picked points using principal component analysis. And this is the disk you see here is colored by the dip direction. Right. Yeah, we also have a color legend for that. So below 0, it's a dark blue, and below 45 degrees, it will be red. And here are the dip and strike values. So the actual dipping angle is 6.5 degrees. And we also compute the dip and strike orientation depending on the north vector. We'll do this a couple of times. Okay, it's really bad. And yeah, it's not supposed to dip in this direction. And after that, we can also export our annotation data. Yeah, let's put it into hidden. And opening this. It does look like that. So you get different properties, also dip and strike azimuths, and also arrow values, which are empty here now. I think they're just turned off at the moment. So yeah, this already concludes our demonstration of this data set. So I will just move on to the Jezero Crater site, showing a large-scale orbital data set. So, Jezero. So this is a top-down view oriented with north is up, and I already prepared some bookmarks here. Here you can see all the surfaces. So these are the different tiles of this high-res reconstruction. We can go to the delta entrance here on the left. We can also see the level of detail, which is much more important here. So here in the vicinity, we load higher detail, and yeah, it also takes some time. And then we can move over to this crater here. So now it makes a bit more sense to show these projection modes. Like for instance, this is the sky projection. Yeah. So it goes basically into the crater, while the linear one is just a connection like this. We can also check the resolution, for instance, of this data set. We select the surface here, then switch to the line mode. So this is the geometrical resolution you can see here. And you can just check how big one grid cell is. And we have a resolution here of 1.8 meters. Big surface we can also deselect again. And look at this from top down. Scene to show you, this time working with more than one OPC. Technically, these are also more than one OPC, but it's only one surface. So we are now looking at Victoria crater with OPC stemming from multiple sensors or algorithms. Oh, yeah. Just take a second. So here we can see reconstruction from HiRISE. We also have super resolution reconstruction here. Just overlaid that. So when we go closer, we can see that these two reconstructions are actually at the same positions. So we employ our so-called parity rendering technique. So this just overrides the depth testing of the graphics card and just overlays this here. We can also see the quality difference between HiRISE and HiRISE Super Res, especially showing that they could remove most of the crater rim shadow. And then we have one more. Oh, no, that's wrong, sorry. So, and now we also add the rover reconstruction, which needs to have priority 2. So now we have HiRISE, on top of that HiRISE Super Res, and on top of that we have white baseline stereo reconstruction of Cape Desire. And there's also an annotation, geological interpretation provided by Robert Barnes of this data set. Here again with dip and strike values, also for surface delineations, and here we have a lot of crossbed measurements. We are already at the Outlook section of this demonstration, so I will show you a prototype. I have to show you a prototype version of Pro3D showing the MINERVA functionality.
Thomas, if I can briefly step in here, you were
almost done. I'm sorry.
You were talking about the super resolution. We need to say that the super resolution has been produced by Peter group of MSSL in the PRO3D project. So they are still generating such products, and we're happy to receive those for closing the gap between the satellite image resolution and the rover image resolution.
Yeah, exactly. There's really a big difference in resolution. It's much easier to fit the rover reconstructions to the large scale reconstruction. So what we can see here is the Gale crater. Oh, sorry. Gale crater area with the Curiosity traverse, not the complete one, but as far as we have products. This one is missing for some reason, but don't worry. And now we will close in on Sol 1087 of the Curiosity mission. What we can see here actually is are the different products. So in In light red, we have the left mast cam camera, and the dark red is the right one. So when we hover over here, we can see the different frustrums of the cameras taking the image products. Here in green, we also have the CamLib instrument, and the blue ones are the nav cams, which you can identify by the very wide frustum. So we'll just select these ones here and filter to them. So let's look at this. So you can actually see that there are 5 laser pulses going from the CamLib instrument. And we can also make a lookup for image data, which is a bit similar to what the Astro tool does. I can select this point here. Oh, sorry. Oh no, it worked. So this is the capturing array of the left mast cam, and here you have the sum of these images taken by the right one, containing this point. And when you click on an image here, it gets overlaid. So this is still a prototype. This is not perfect here, but this is a prototype approaching linking 2D original images to the 3D reconstructions. Yeah. And as a last item of this talk, I will show you a video of the viewplanner, which is a bit the counterpart to the MINERVA functionality. So before you want, it's actually to evaluate where to put the rover and how to capture something, instead of looking up what the rover captured. So we pick 2 points here, position of the rover and where it looks at. And this is kind of a super rover, which has all the instruments of Curiosity and ExoMars, and also all emulators. And now we selected the left wide angle PanCam instrument, and what the PanCam sees is displayed here on the right. We can adjust PTU values, and we can also do the same annotations I showed you before in this instrument view, which gives us a possibility to just reconstruct the footprint on the surface. So this has a reason why we are doing this, because now we switch to the HRC, the high resolution camera of the Rosalind Franklin rover, and check how these 2 footprints overlap. This is also still a prototype version. And of course, we also have the Mastcam C camera with zooming capabilities, which is a widescreen camera, not the quadratic one, square one. And we can zoom in and out here. So yeah, that's the demonstration of all the current and some future capabilities of Pro3D.